Welcome to the deep dive. Today, we're taking a plunge into something pretty fundamental, the operating manual for our universe, you might say.
That sounds about right.
Specifically, Richard Feynman's Nobel-winning idea, Quantum Electrodynamics, or QED. He actually called it the strange theory of light and matter.
And, well, strange is putting it mildly sometimes. But if you need an instruction manual, this is kind of the main one. QED covers almost everything you see and touch daily.
Like what exactly?
Oh, why steel is hard, how electricity works, why things burn, basically all of chemistry. It's the language of how light and electrons get along.
Or don't.
So it really is the foundation. It explains almost everything except, gravity.
Yeah, gravity's still the odd one out. And stuff happening right inside the atomic nucleus, like radioactivity. QED handles the rest, the electromagnetic world.
Okay, but there's a catch, right? A big warning label Feynman himself put on it.
Absolutely. He was very clear. The rules QED uses, the way it describes nature, it seems like utter nonsense from our everyday perspective. Right, like common sense just goes out the window.
Exactly. So the goal here isn't really to understand in the usual sense, like why nature picked these rules. Nobody truly gets the why. The goal is just to learn the rules, learn the recipe, so we can calculate how things behave. And honestly, it's the most successful recipe physics has ever found.
So where do we start? The obvious problem, maybe. Light itself?
Perfect place. We've known for ages light acts like waves, right? You see
Oh.
interference patterns, diffraction, wave behavior.
But then, if you turn the light way, way down, like super dim, and use a sensitive detector...
You get clicks, discrete packets hitting the detector. And the clicks don't get softer, they just get less frequent. Particles.
Photons.
Those are the photons. So you have this built-in contradiction, waves sometimes, particles other times. The big question isn't which is it, it's how do we make rules that handle both?
Okay, let's take the simplest case imaginable. You shine light straight at a flat piece of glass, 90-degree angle.
Right. Clean, simple setup.
Now, common sense, thinking about particles, says an individual photon either bounces off, reflects, or goes straight through. One or the other.
Seems logical. But when you measure it, only about 4% of the photons actually reflect back. The other 96% go through.
And the real kicker isn't the 4% average, it's the single photon, isn't it? How does one photon, before it even hits the glass, decide if it's going to be in the 4% reflection group or the 96% transmission group?
That's the mystery. And QED's answer is, well, it's deeply weird. It says you cannot predict what any single photon will do, period.
You can only predict the odds, the probability.
Exactly. And that's where Feynman's famous little arrow comes into play. It's not a real arrow, obviously. It's a mathematical thing called the probability amplitude.
Okay, so this arrow, it has a length and a direction.
Yep. Length tells you sort of how much probability, and direction is crucial for how different possibilities combine. The absolute core rule of QED calculation is this. The probability you actually measure for something happening is the square of the length of the final arrow you calculate for it.
Okay, so back to the glass. We measure 4% reflection. That's a probability of 0.04. So the arrow for reflection must have a length of 0.2, because 0.2 times 0.2 is 0.04.
Precisely. That 0.2 length arrow, that's the quantum reality we're calculating, not the 4% directly.
All right, now let's make it trickier. Bring in the wave part. Instead of one surface, think about a thin film, like oil on a puddle.
Good example. Now you've got two surfaces close together. The top of the oil film and the bottom of the oil film where it meets the water.
So naively, if you get 4% reflection from the top surface and maybe another 4% from the bottom surface, you'd think they just add up, right? Like 8% total.
That would be the simple particle picture. But nope, that's not what happens at all.
What does happen?
The amount of reflection goes totally wild. It depends critically on the exact thickness of that oil film. It can swing from basically zero reflection.
Zero, like none at all.
None at all.
Yeah.
All the way up to 16% reflection.
Yeah.
That oscillation, 0 to 16%, just based on thickness, that screams wave interference. Simple particles shouldn't care about thickness that way.
So the QED rules, the arrows, have to explain this interference. How does that work?
It comes down to another core QED principle, how you combine possibilities.
Okay.
The rule is, if an event can happen in more than one way, say path A or path B, you calculate the arrow for path A, you calculate the arrow for path B, and then you add the arrows geometrically.
Yeah.
Like vectors, head to tail.
And the length of that final combined arrow squared gives a total probability.
That's the rule. So for the thin film, the two ways are reflecting off the front surface, arrow 1, or going through, reflecting off the back surface and coming back out, arrow 2.
Okay, so we had arrow 1 and arrow 2, but for them to interfere, to sometimes cancel out and sometimes reinforce, their directions must matter. What determines the direction?
Time. It's all about the time it takes. Feynman used the idea of a tiny hypothetical stopwatch, or like a clock hand, spinning incredibly fast.
A clock hand.
Yeah, think of it like this. As the photon travels, this imaginary clock hand is just whirling around. For red light, it spins about 15,000 times for every centimeter the photon moves. It's ridiculously fast.
Okay.
The final direction of the arrow for any path is determined by where that clock hand is pointing when the photon arrives or interacts.
Right. So for the thin film, arrow 1, the front surface reflection, its length is 0.2, we know that. What about its direction?
Here's a weird quirk. For reflection off the front surface, going from air to a denser medium like oil or glass, the arrow's direction is always flipped 180 degrees from wherever the clock hand happens to point upon arrival.
Flipped. Why?
No good why. It's just one of the fundamental rules you have to accept to make the calculations match reality, a 180-degree phase shift on reflection from a denser medium.
Okay, rule noted. What about arrow 2 from the back surface?
Arrow 2 also has a length around 0.2. It's slightly more complex, but let's keep it simple. Crucially, its direction is not flipped. It points exactly where the clock hand points when the photon reflects off that back surface.
Ah, so the path for arrow 2 is longer. It has to go down through the oil and back up.
Exactly. That extra travel distance means the little clock hand does some extra spinning.
So the clock hand for arrow 2 will be pointing in a different direction compared to arrow 1 when the photon emerges.
Precisely. And that difference in direction is everything. If the oil film thickness is just right, the extra travel time for arrow 2 rotates its clock hand, and thus its arrow, by exactly 180 degrees relative to arrow 1's final direction after it's flipped.
So arrow 1 is flipped, and arrow 2 is rotated 180 degrees. They point in opposite directions.
Yep. You add two arrows of equal length pointing opposite ways. They cancel completely. Resultant arrow length, 0. Square it, 0 probability, 0% reflection.
Wow. Okay. And if you change the thickness just a tiny bit,
Then the rotation for arrow 2 isn't 180 degrees anymore. Maybe it rotates until it lines up perfectly with the flipped arrow 1.
so they point the same way.
Right. Now you add two 0.2 length arrows pointing the same way. The total length is 0.4. Square that.
0.16, that's 16% reflection.
And that's it. That oscillation between 0% and 16% based on thickness is perfectly explained by adding these little arrows whose directions depend on travel time.
And this is why we see colors in oil slicks or soap bubbles, iridescence.
Exactly that. Different colors of light are slightly different frequencies, which means their little clock hands spin at slightly different speeds. So a thickness that causes red light arrows to cancel might cause blue light arrows to add up strongly. As the thickness changes, or you view it from different angles, the colors shift. It's beautiful wave interference derived from these arrow rules.
Okay, that's pretty convincing for thin films, but can these strange rules explain something really basic, like light reflecting off a normal mirror? We learn in school angle of incidence equals angle of reflection, shortest path.
Right, the classical view. Seems simple. But QED says, hold on, it's much weirder underneath. To calculate the probability of a photon going from a source to a detector by bouncing off a mirror,
You have to
consider the photon reflecting off every single point on the mirror surface. Not just the one spot predicted by classical optics. Every point. The middle, the edges, everywhere.
Wait, every point. Even paths that look ridiculously long reflecting off the far corner.
Even those. In fact, technically, you sum over paths that miss the mirror too, though those contributions turn out to be negligible. The rule is sum all possible paths.
That sounds computationally impossible. Infinite paths.
It would be, except for a wonderful bit of cancellation. Think about the paths hitting the mirror way out near the edges. Compared to the central path, they take significantly longer.
Meaning their little clock hands spin much, much more.
A lot more. So the arrows for paths, just slightly different from each other out near the edges, end up pointing in wildly different directions because of that rapid change in travel time.
And if you add up a whole bunch of arrows pointing in random directions,
They mostly cancel each other out. They sum to essentially nothing, like a random walk ending up back near the start.
but what about the paths near the center of the mirror? The ones very close to that classical shortest time path.
For those paths, a small change in position on the mirror makes almost no difference to the total travel time. They all take very, very similar amounts of time.
So their clock hands end up pointing in almost the exact same direction.
Precisely. These arrows add up constructively, they reinforce each other, all the other paths cancel out, leaving only the contribution from the region where the time taken is minimal, which happens to be exactly where the angle of incidence equals the angle of reflection.
So QED actually derives the classical law of reflection from this bizarre sum over all paths rule.
It does. Classical optics emerges as a large-scale approximation of this deeper quantum process.
Okay, let's use that idea. Refraction. We're taught light slows down in glass or water, index of refraction, right? How does QED handle that with arrows and clocks?
Well, first, the photon itself in the vacuum between atoms always travels at c, the speed of light. It never actually slows down.
But it looks slower when it goes through glass. Why?
Because it's not just traveling through the glass. It's interacting. As the photon moves through the material, it's constantly interacting with the electrons in the atoms of the glass. Think of it as a series of absorptions and re-emissions, or scattering events.
So it's not a straight shot, it's like bumping around.
Sort of. You have to sum the arrows for all these possible interaction paths inside the glass. Each little interaction adds a tiny turn to the overall arrow's direction.
Like the clock hand gets delayed or turned a bit extra at each step.
Exactly. The net effect, when you sum up all these tiny turns from all the interactions along the path through the glass, is that the final arrow for the journey through the glass is rotated compared to what it would have been for the same distance in a vacuum.
And a rotation of the final arrow looks like?
It looks exactly like the photon took longer to get there. It manifests as a delay, which we interpret macroscopically as the light having slowed down. It's not slower speed, it's accumulated phase shift from interactions.
That's elegant. So the index of refraction is really about the density of electrons and how strongly they interact, causing this cumulative rotation.
That's the essence of it.
Yeah.
Now, all this complexity, reflection, interference, refraction, Feynman showed it all boils down to just three fundamental actions, like the basic letters of the electromagnetic alphabet.
Only three, seriously?
There's three core things that can happen, each with its own associated arrow. Action one, a photon travels from point A to point B. We can call its arrow FA.
Wait. Yeah.
Action 2. An electron travels from point A to point B. Its arrow is EAB.
Got it.
Action 3. The crucial one. An electron emits or absorbs a photon. This is the interaction vertex. It has a fundamental strength, a coupling constant, usually called J or E. But in Feynman's popular description, he used a simple number B, which is about negative 0.1.
Minus 0.1. That seems small.
It is small, and that's incredibly important. It represents the fundamental charge, the strength of the electromagnetic interaction. Now, remember the rule for combining possibilities.
If it's path A or R, path B, you add the arrows.
Right. But what if an event happens sequentially? Like step 1 and D and then step 2.
Ah, okay. What's the rule for A and D?
You multiply the arrows, which means you multiply their lengths and you add their angles, the clock hand directions.
Okay, multiply lengths, add angles. So if a process involves, say, an electron emitting a photon, 1B interaction, and then reabsorbing it, a second B interaction.
That path contribution involves multiplying the arrows, so its overall strength gets a factor of B times B, which is 1.1 times 0.1.01.
So paths with more interactions get suppressed really quickly.
Very quickly. A path with 4 interactions has a strength factor of B for $4, which is 0.00001. This is why physicists can often get incredibly accurate results by calculating just the simplest paths, the ones with only 1 or 2 interactions. The more complex ones contribute progressively less.
Makes sense. Now, you mentioned electrons traveling. What about antimatter? Where do positrons fit in?
This is one of the most mind-bending, beautiful parts of QED. When you write down the math for an electron traveling from A to B using these arrow rules, the equations work just as well if the electron is moving backward in time.
Backward in time? Seriously, like time travel?
Mathematically, yes. On a space-time diagram, you can draw an electron path moving from a later time back to an earlier time. And the QED calculation for that path.
What about it?
It turns out to be mathematically identical to the calculation for a positron, the electron's antiparticle, with a positive charge moving forward in time between those same points.
Whoa. So an electron going backward in time is a positron going forward in time, as far as the math is concerned.
Exactly. It's not just a trick. It's a deep consequence. The existence of antimatter just falls out of requiring the theory to be consistent with relativity and quantum mechanics. Every particle having an antiparticle is baked into the structure. Photons, interestingly, are their own antiparticles.
That's incredible. Okay, before we get to the grand finale, the big proof, there's one more piece. Chemistry. How does QED explain why atoms don't just collapse, why we have the periodic table, different elements, the Pauli exclusion principle?
Ah, yes. Crucial point. It involves another twist on the arrow addition rule, specifically for identical particles like electrons. If you have two electrons, you're calculating a process where they could end up swapped.
Like electron 1 goes here, and electron 2 goes there, electron 2 goes here, and electron 1 goes there.
Precisely. Those are two possible ways for the event to happen. So normally you'd add their arrows. But for electrons and other fermions, there's a minus sign involved. You have to subtract the arrow for the swapped path from the arrow for the unswapped path.
How do you subtract arrows?
It just means you rotate one of the arrows by 180 degrees before you add them head to tail.
Okay, so what if the two electrons are trying to end up in the exact same state, at the exact same point in space-time?
Then the unswapped path and the swapped path are identical. Their arrows are identical.
So you take arrow A and you subtract arrow A.
Which means you take arrow A, flip it 180 degrees, and add it to arrow A. They point in opposite directions.
They perfectly cancel out. The total arrow length is 0.
Zero length. Zero probability. That's the Pauli exclusion principle, derived from QED rules. Two identical electrons cannot occupy the same quantum state.
And that's why electrons fill up shells in atoms, giving us structure, chemistry, materials.
It's why matter takes up space. It's why insulators insulate and metals conduct. Without that minus sign in the arrow rule for electrons, the universe would be unimaginably different, likely just a uniform mush.
Mind-boggling. Okay, so QED explains interference, reflection, refraction, antimatter chemistry.
Oh.
What's the ultimate test? The proof that this strange theory is really right.
The benchmark, the gold standard, is predicting the magnetism of a single electron, its magnetic moment.
Okay, what did older theories predict?
Dirac's relativistic quantum mechanics, a precursor to QED, predicted the value should be exactly 1.0 in certain units. Simple, elegant.
But experiments
Experiments got incredibly precise, and they found the value wasn't exactly 1, it was slightly more, about 1.00118. A tiny difference, but definitely there.
So could QED explain that tiny extra bit?
Yes, that's its crowning achievement. QED says the simple path of the electron gives the value 1.0, but you have to include more complex paths allowed by the rules.
Right.
Like the path where the electron as it travels along emits a photon, and then a moment later reabsorbs that same photon. A little quantum fluctuation.
That path involves two interactions, right? Emission and absorption. So it involves that small number b twice.
Exactly. Its contribution is proportional to BD2, or about 0.01. Calculating that contribution gives almost exactly the needed correction.
Almost.
Well, you can then include even more complex paths. Paths where the electron emits two photons and reabsorbs them, or the photon briefly turns into an electron-positron pair. These involve T47, FIT, T-SIGA-N, BD, all or other terms.
Calculating those must be insanely difficult.
Oh, it requires monumental effort. Calculating the B&L terms involves summing literally billions of distinct Feynman diagrams, needing massive supercomputer time.
But they did it. And what's the result?
The agreement is just stunning. The QED theoretical prediction is 1.0011596546, with a tiny uncertainty in the last digits.
And the experimental measurement.
The latest experimental value is 1.001159652221, again with a tiny uncertainty. They agree to an unprecedented level of precision.
How precise is that, really?
Feynman loved this analogy. It's like measuring the distance from Los Angeles to New York City, about 4,800 kilometers, and getting it right to within the width of a single human hair.
That is absolutely insane.
It's arguably the most precisely verified prediction in the history of science. It tells us that, as strange as QED is, it must be capturing something profoundly true about reality.
So stepping back then, what's the big takeaway from all this strangeness?
I think it's that the reality you perceive, the simple things like light going in straight lines or bouncing predictably off mirrors, that's just the surface layer. It's the result of summing up an unbelievable number of underlying quantum possibilities, these little arrows representing paths.
Paths that include photons going faster than light, electrons going backward in time, all the nonsense.
All the nonsense. Nature, at its deepest level accessible to us, seems to operate on probability amplitudes, summing over all conceivable ways something could happen, no matter how bizarre, weighted by these complex numbers, these arrows. And the results we see are just the outcome of that vast hidden calculation.
The most precise, powerful theory we have is built on rules that defy our intuition, using just 3 basic actions to generate all this complexity.
Pretty much. And maybe here's a final thought to leave you with.
The
very stability of the world around you, the fact that things seem solid and follow predictable laws most of the time.
Yeah.
It might just be the result of near-perfect cancellations. trillions upon trillions of quantum possibilities constantly adding up and subtracting, interfering destructively, leaving behind only the simple patterns we call reality. Maybe solidity is just the outcome of an ongoing, infinitely complex quantum stalemate.
Calculated nonsense holding everything together. Thank you for joining us for the deep dive.